Everyone. This is the start of the last session today, and I am happy to welcome Manvel Avetisyan from Sberbank, who also was our speaker at the first online edition at DataFest. And yeah, a really interesting topic about COVID and medical application. Manvel, take it away.
Thank you. I'm very glad to be here, and I'm very happy that such an event like DataFest is organized and there is such a large interest. That's truly amazing, and let's continue with going. Today I'm...
So you guys wouldn't hear the fun part. Yeah, so today I will talk about 3 solutions that we developed to fight global pandemic. All of them are practical and they were aimed to solve concrete, well-defined problems in practical applications. So all of these researches are published in form of papers. Some of them are under review, some of them are already accepted, but all of them are available on arXiv. So the first project that I will talk about is a system to interpret CT scans of patients who are under suspicion of having COVID disease. So let's start with the data. The data is CT scans. CT scan is actually a collection of slices. Each slice is 512 by 512, and it's several hundred slices which form a 3-dimensional tensor, which is a representation of the body. Each pixel in each voxel in that tensor is valued with Hounsfield units. It's a unit of rentgenological depth, rentgenological so basically it's our rentgenological unit. It's not that important for us. We collected our own data set from various institutions who were treating COVID-19 patients. Overall, it was less than 100 CT images. Each image contained several hundred slices, and basically we took all the slices which contained lungs and did segmentation with help of experienced radiologists. Here you can see on the left is a slice from such a CT scan, and on the right you see a mask which shows where is places in the lung which are COVID-19 affected areas. Other than training data set, we collected a separate experimental subset which were used in several different ways, and I will be speaking about them a little bit later. But basically, the first part was used to assess the quality of segmentation. Second part was used to assess the quality of prediction of the ratio of the volume which is affected by COVID-19. And the third one was used to classify the severity of the disease. So actually we didn't have a lot of time to go deep into the research. Basically what we did, we built several models, each of which performs the same task. And then we built an ensemble of such models. So all of them are built in a very similar fashion. It's actually a UNet, which has a deep classification neural network for encoder part and a regular UNet for decoder part. Here we show quality, intersection by union, dice coefficient for each model and for the ensemble models. Actually, all of the models use different kind of normalization, but it's the most popular normalization that we used. Basically, we normalized values with our scale and data that are written in typo, and then we just drop everything that we don't like, and everything that we don't like is below 0.505 and above 0.505. Another task that we did is we did a model that segments lungs. It's actually not a very hard task, and we used several data sets to build a model that worked well. And we used that model together with a segmentation model. So what we do we'll have a single CT scan slice as an input. We would segment lungs on that CT scan, keep only that, and then we will pass it through these ensembles of neural networks, each of which will give a prediction, and then we will ensemble that, and we will get a final prediction that will output. For ensembling, we used this hand-built algorithm, which looks a little bit ad hoc, but overall it worked pretty good for us. We did the comparisons with radiologists for the test of segmentation of areas on the lungs that are affected by COVID, and our model was better than 5 from out of 6 of radiologists, which is pretty good result. Another task was the estimation of lesion share. It means like a ratio of the tissue that is affected by COVID-19. Here, our results were still better than most of radiologists. It showed that radiologists are very bad at estimating lesion share, that the tasks that they are required to do regularly, because they, like human beings, do not have an ability to integrate three-dimensional volumes. So actually our research showed that the diagnostic criteria that is used to treat people is not that objective, actually. Here we see that radiologists have more deviating predictions as lesion share gets bigger. And yeah, the standard deviation gets big. And the last task is a prediction of severity of the disease. Here again we showed pretty promising results. So basically we built a pretty good model that worked pretty well across all the tasks. If you are interested, just read the paper. Again, we compared our model with baselines. That at that moment there were not a lot of baselines available, and again we performed pretty good. The second project that we did recently is an app for iPhone or Android, which everybody can use to assess a risk of COVID-19 using recordings of breath, voice, and cough. So at that moment, actually, it was known that it is possible to figure out if whether a person has a COVID-19 or not from the cough only. But there were not a lot of good data sets available. However, we found this public data set that was collected by people who are it was collected by one of hospitals, and they would call everybody, call their clients and ask them to cough using phone calls. And then also they used a telegram for the same task. Another part of our system is prediction of the probability of disease from common symptoms. We extracted those symptoms from our data sets that we have, and then we use them to get more input from the patient. So this is the scheme of the model. We will get a recording for somebody from a user. Then we will segment cough sounds on that recordings, and then we will extract various features: MEL spectrograms, cochleograms, VGG embeddings. We will get symptoms from the patients, and we will bag and ensemble them, and we will get 3 possible results. We are sure that there is no COVID. We have high probability. We think that they may be COVID, and we are not certain. This is the ROC curve for cough detector, which worked pretty fine, and it's actually not a very hard task. We combined several publicly available data sets to build training and test sets for that task. And basically our model worked best on that COVID-19 dataset that was collected by hospitals, and we stick with that, but later we collected our own datasets. Basically this model worked pretty good as well. It worked better or comparable to gradient boosted models. We tried different ensembles to maximize, in some cases, precision, in some cases, recall, in some cases, accuracy for different practical tasks. Overall, we built an ensemble that was used later in production. After we built first prototype, we asked a lot of users to use that. And then we built a histogram of probabilities given self-reported status, whether somebody has a COVID or doesn't have. We used that to select this middle ground where we are not sure whether somebody has COVID or doesn't have. This is a probability of cough recording. So in a lot of cases we were getting bad sounds, like the sounds that are not actually coughs. So our decision to build a separate segmentation model that will select parts of the recording which are actually cough sounds was good one. And after that we built this prototype that basically everybody can use to assess the risk of COVID-19. Nowadays it's available on App Store and Google Play, and you guys may try it and use it. The third project is the one that I've not participated directly. It's a prediction of probability of complications from COVID-19 for patients admitted in healthcare units. Actually, doctors came to us with this problem because from their point of view, it was pretty hard to determine who would be from patients who are admitted to hospitals, who would be moved to ICU units. And they wanted us to build a model that will help them to predict that. So the target was to predict the probability of moving a patient to ICU unit given the recordings that they have in electronic health record.
Sorry, what's ICU?
Intensive care unit. We used anonymized textual data from EHR. We used a lot of textual data that we had radiology reports, we had lab reports, we had diagnosis, and we concatenated that to one big string of text string that we used to build a classifier. Our data contained a lot of different data, but overall we decided that we'll just concatenate it and just feed it to the neural network, and it will do the job for us. We used two data sets, two major institutions in Russia, to build this model. So the data was pretty, the variability of data was pretty big, but nevertheless we still decided to build one model that does everything. This is the graph of outcomes in the pilot study. Basically, we will have patients. We will declare who has higher risk of being moved to ICU, and overall it worked pretty well. And during the patient, we were able to detect people who would be moved to ICU units. Overall, doctors were pretty happy with our research. As far as we know, they are still using it. But unfortunately, we do not have statistics and no to present right now. That's it. Thank you.
Questions?
Thank you for the interesting talk. I just have one question. So your model seems to work for predicting ICU tickets. And do you have an idea what features were the most predictive for the performance?
In this project, we didn't try to assess that, but previously we tried to assess which features does a bird use to predict one of other outcomes, and we couldn't get sufficiently easy to understand and representative idea of that. So we don't know. The only thing that we know is that it works, but how it works, we don't know.
Yeah, I guess it just comes back to AI explainability then.
Yeah. Actually, one explainability of such models is a pretty strong problem in medical AI, and we did some work on that, but the results for such kind of deep models are just not satisfactory good.
Okay, thanks.
Thank you.
So I noticed that some data sets are not really big, so I'm interested in did you train your models from scratch, or you use heavy augmentation, or you fine-tune some pre-existing models?
So data in medical AI is really not that, we usually don't have that much data. For the CT scan segmentation task, we obviously used weights that we got from ImageNet models. For the CAF project, we didn't use any pre-training at all. For the ICU prediction project, we used, I guess it was RU-EHR BERT. It's a BERT trained on EHR text.
And do you use data augmentation for your tasks?
Not really. Yeah, obviously again, for the first project, for city segmentation task, we use heavy augmentation. For CAF, we used a lot of augmentation, which consisted of various transformations of CAF recordings. For the last project, we didn't use any augmentation at all.
So, additional questions?